On the morning of August 10th, just last year, a mountainside in southeast Alaska gave way and sent a wall of water climbing 1,578 feet up the opposite slope. Sit with that number for a second. That's 481 meta RS, taller than the Empire State Building by a wide margin. It happened inside a fjord called Tracy Arm, roughly 80 miles south of Juneau, at about 2:65 in the morning. Nobody died, and the only reason for the is timing. The tour boats that sail into that fjord every single summer day simply hadn't arrived yet. That wave is now the second largest ever recorded anywhere on the planet. The largest one also happened in Alaska, the same type of event, 67 years earlier. So let me hand you the answer up front, because it's the part that actually matters, and I don't want you sitting through 20 minutes just to get there. Both of these were landslide tsunamis, and that's a completely different animal from the earthquake tsunamis you've probably seen covered on the news. A mountainside collapses into deep water. That water has nowhere else to go, so it goes up. And in Alaska, these events are becoming more frequent for a reason scientists can point to directly. The glaciers that used to physically brace those mountainsides in place are thinning out. Once the ice disappears, the support structure disappears right along with it. Here's the roadmap for what we're covering. First, exactly what happened at Tracy Arm last August, because the numbers involved are genuinely extraordinary. Then we'll go back to the 1958 event that still holds the world record to this day. After that, I'll walk you through the mechanism in plain, ordinary language so you actually understand why a shrinking glacier can cause an entire mountainside to fail. Then we'll get into Barry Arm, the slope in Prince William Sound that the USGS has had under close watch since 2020, sitting about 30 miles from a town of roughly 200 p Opal, and what their actual model says, which, spoiler, is not what most corners of the internet seem to think it says. And at the very end, I'll cover what any of this practically means if you or someone in your family happens to have an Alaska cruise booked. Before we get into Tracy Arm, though, I want to ask you something, and it's a genuine question, not just a formality to pad the intro. If you've ever been on a small boat glacier tour in Alaska, whether that is Tracy Arm, College Fjord, Kenai Fjords, anywhere like that, tell me in the comments where you went and roughly what year it was. I'm asking this seriously, because people who have actually stood inside those inlets carry a sense of scale that no map or photograph can really give you. I read every single comment. Now, back to Tracy Arm. A fjord, for anyone unfamiliar, is a valley that a glacier carved out over thousands of years, when the ocean later flooded once the ice retreated far enough. The walls inside are close together, and brutally steep, sheer granite rising almost straight out of the water, and the water itself runs deep right up against that rock. There's no shallow shelf out there, no beach, nothing to absorb or soften anything that comes crashing down. At the head of Tracy Arm sits South Sawyer Glacier. On the slope above that glacier, something in the range of 64 million cubic meters of rock detached from the mountain in a single event. The USGS put the preliminary volume estimate as high, H as 100 million cubic meters, or roughly 130 million cubic yards. Even taking the lower figure, you're talking about enough rock to fill a large sports stadium several dozen times over. That mass slammed into the water and produced an initial breaking wave roughly 328 feet high, about 100 meters, moving at speeds exceeding 156 miles per hour. That's just the starting wave. From there, it ran up the opposite wall of the fjord to a full 481 meters. USGS field crews measured trim lines, essentially scar lines in the vegetation, between 470 and 500 meters directly across from the slide, which works out to somewhere between 500 and 1,600 feet of scoured bare rock where forest used to stand. Farther down the fjord, at Sawyer Island, the wave had dropped to around 100 feet. And by the time it finally reached the tide gauge back in Juneau, it registered at just 14 inches, about 36 centimeters. Put those two figures side by side, because that GEP tells you almost everything about how this type of tsunami behaves. Roughly 1 to 1,500 feet near the source, 14 inches, 80 miles away. It's absolutely savage right where it originates, and it burns off its energy fast once it escapes the narrow channel. There were people inside that fjord when it happened. A group of kayakers had set up camp on Harbor Island that night. Nobody was hurt, but the wave tore straight through their campsite and swept their gear out into the water. 6 different sea cruise lines adjusted their Alaska itineraries in the aftermath. The findings were eventually published in the journal Science. And here's the part that should genuinely unsettle you. Nobody saw this one coming, because nobody was actually watching that particular slope. There was no instrument monitoring it at all. The way an event like this usually gets caught is entirely after the fact. Large landslides shake the ground enough that seismometers positioned hundreds of miles away record a long, low rumble that doesn't look anything like a typical earthquake signature. It builds gradually and fades gradually instead of cracking sharply. Researchers then work backward from that seismic signal, fly a team in, and measure the trim lines by hand on the ground. That's the exact sequence that plays. Yeet out at Tracy Arm. Detection first, then a field team, then eventually a published paper. I'll circle back to this contrast in a moment because Barry Arm represents the exact opposite situation, and that comparison is probably the single most useful thing in this entire video. The slope that failed at Tracy Arm had been quietly preconditioned for this, and that detail is what turns this from an isolated curiosity into a recognizable pattern. South Sawyer Glacier has been steadily retreating, and as it pulled back, it left that rock face standing there without the ice that used to be pressed firmly against it. Which brings us to 1958. In July of that year, an earthquake somewhere between magnitude 7.8 and 8.3 ruptured the Fairweather Fault in southeast Alaska. The shaking dislodged roughly 30 million cubic meters of rock off a cliff at the head of a bay called Lituya Bay, sending it crashing into a narrow inlet known as Gilbert Inlet. The water inside that inlet surged up 524 meters, 1,719 feet. That remains the highest wave run-up ever recorded in human history, and it hasn't been surpassed in 67 years. To picture it, imagine standing at the base of a 50-story building and watching water sweep clean over the roof. 5 people died that night. 3 fishing boats happened to be anchored in Lituya Bay. 1 sank, taking 2 people down with it. Another was physically carried up and over the trees growing on the spit at the mouth of the bay, over the tree tops entirely. And the couple aboard survived to describe exactly what happened. The 3rd boat's crew also lived to recount it. The physical evidence is still visible today. The wave stripped the forest clean off the bay's walls in a sharp, unmistakable line, and you can still see precisely where the old-growth trees stop and the younger regrowth begins. Geologists studying those same trim lines have identified at least 4 additional major waves in Lituya Bay, stretching back into the 1800s. That particular inlet simply does this. It's practically built for it. I want to be precise here about exactly what that world record actually measures, because it gets misreported constantly online. That 1,719 feet is a run-up measurement. What that means is it's the elevation the water reached as it climbed the far slope, determined on the ground by exactly where the trees stopped growing. There was no 700-foot wall of water physically traveling across Lituya Bay. An enormous surge of water got violently shoved sideways into a wall of rock and rode up the face of it, and the trim line simply marks the highest point it reached. That distinction explains why a wave can register 1,700 feet at its source and shrink down to a rounding error just a couple of bays over. It doesn't make the event any less lethal for anyone caught inside that particular inlet. It just tells you exactly where the real danger concentrates, close, fast, and inside the fjord itself. Alaska experiences more of these events than anywhere else on Earth, and the reason ultimately comes down to ice. Start with what a glacier physically does inside a mountain valley. It's a mass of ice, sometimes hundreds of feet thick, pressed firmly against the valley walls on both sides. It leans again. Saint the rock, and the rock leans back. The two hold each other up in a kind of standoff. Then the glacier begins thinning and retreating, and suddenly the ice that used to be braced against that wall simply isn't there anymore. What's left behind is an extremely steep rock face, one fractured after. Are thousands of years of ice grinding against it? That used to be supported, and suddenly isn't. The technical term for this process is debuttressing. That's essentially the entire mechanism in a nutshell. Remove the brace holding the wall up, and the wall has to find out the hard way whether it can actually stand on its own. 2 additional factors stack right on top of that. Up in the high country, there's permafrost, ground that stays frozen year-round, and the ice sitting inside cracks in the rock is doing part of the job of gluing that rock together structurally. As that permafrost thaws, joints that used to be frozen solid start opening up, and increasingly heavy rainfall then pushes water directly into those same joints. Water sitting inside a crack carries real weight and real pressure, and it actively pries the rock apart. None of this is exotic science. It's the exact same reason a backyard retaining wall eventually fails. You removed whatever was holding it in place, and then you let water get in behind it. There's one more piece to this puzzle, and it has less to do with the rock and more to do with the shape of the container it falls into. Out in the open ocean, a wave spreads outward in every direction and loses height rapidly. Inside a fjord, it simply can't do that. The walls sit close to ether. The water runs deep, and all of that energy gets trapped inside a narrow trench with nowhere to spread sideways, so it's forced upward instead. That's exactly why the 2 tallest waves ever measured on Earth both occurred inside inlets narrow enough that you could nearly throw a rock across them. And it's also why a wave that measured roughly 1,200 feet at Tracy Arm had shrunk down to just 14 inches by the time it reached open water near Juneau. The fjord creates the wave E, and then the fjord contains it. You can see the fingerprint of that pattern clearly in the data. High Country News, summarizing the underlying research, put it bluntly, the evidence points to a sharp uptick in landslide-generated tsunamis across Alaska over roughly the last decade or more, and that's simply a tally of events that have already happened. Barry Arm is the slope people are currently watching closely on a screen somewhere right now as you're hearing this. Barry Arm is an inlet inside Prince William Sound in south-central Alaska, roughly 30 miles northeast of a small town called Whittier. Whittier has a year-round population of somewhere around 200 people, and it also happens to be the launch point for dozens of tour operators. Boats leave that harbor constantly throughout the summer season. Above Berry Glacier sits a slab of mountainside geologists refer to as Landslide A. The USGS cites roughly 455 million cubic meters of rock in the portion of the mass sitting right at the glacier's front, with the entire unstable feature closer to 500 million cubic meters total, somewhere around 650 million cubic yards. Compare that to Tracy Arm's 64 million cubic meters, or Lituya Bay's 30 million. Barry Arm is roughly 7 times larger than the slide that hit Tracy Arm. This slope has been moving for a long time. Researchers spotted it in aerial photographs dating back to at least 1935, and possibly as far back as 1913. It really started drawing serious attention in 2020. Between 2010 and 2013, it was moving roughly 85 feet a year. From 2017 onward, that rate dropped to a bit over 4 feet a year. Then, in August 2022, monitoring instruments picked up movement of 41 to 69 millimeters a day, roughly 1.5 inches to nearly 3 inches every single day. If you're getting real value out of this breakdown, subscribing to the channel is genuinely the thing that helps most. And I want to be upfront about exactly what you're signing up for when you do that. I read the actual scientific reports myself. I'll put every source directly on screen. And whenever I get something wrong, I'll say so clearly in the next video. That's the deal. And here's the contrast I promised to come back to. Nobody was watching the slope above Tracy Arm. Barry Arm, by comparison, has been under active observation for 6 years running now. Here's roughly how you actually watch a mountain, because the process is less mysterious than it might sound. The first tool is satellite radar. A satellite passes over the same patch of ground every few days and bounces a radar signal off the surface. By comparing the return from one pass against the next, scientists can measure whether that ground shifted in the meantime, down to a fraction of an inch, all from orbit, without anyone ever setting foot on the actual slope. That's the exact technique that first flagged the Barry Arm feature, and it's how researchers reconstructed those historical movement rates from old satellite imagery. From there, you add physical hardware on site. GPS units bolted directly into the rock that continuously report their own position. Seismometers listening for cracking sounds deep inside the slab. Cameras. Water level sensors down in the fjord itself, so that if something does eventually let go, there's a record showing the wave actually left the source. That last instrument is what's known as the point Doran sensor, and it happens to be the one piece of hardware at Barry RM that's currently offline. All of that data feeds into a public alert level, and that alert level is genuinely the thing worth checking if you're heading up that way. Alert level 1 means baseline conditions, stable or creeping very slowly. It climbs from there as movement accelerates, and it's a public number the state actively updates. Now, back in 2020, an early estimate circulated widely, suggesting a Barry Arm failure could send a 30-foot wave crashing into Whittier. That number is now outdated, and the very people who produced it are the ones who corrected it. The USGS published Open File Report 2021-1071, authored by Barnhart, Jones, George, Coe, and Staley. Using a landslide tsunami model called DCLAW, they ran 4 separate scenarios, the entire slab failing all at once and the slab failing in pieces, at 2 different volume estimates. Looking directly at their results table, 2 numbers stand out as the ones that actually matter. Up in the northern part of the fjord, close to the slide itself, the modeled waves reach roughly 200 meters, about 660 feet. That's essentially the same devastating scale we saw at Tracy Arm and Lituya Bay, and anything on the water up there simply doesn't survive. But 500 meters offshore of Whittier itself in Passage Canal, the modeled wave comes in at just over 2 meters, roughly 7 feet, arriving at around the 26-minute mark, with the first surge of energy reaching town roughly 20 minutes after. The slope first starts moving, 7 feet, not 30. Jonathan Gott, who coordinates the Landslide Hazards Program at the USGS, explained the revision directly. noting that there were a lot of unknowns in the early estimates and that with newer landscape and seaflow, core data now available, researchers have a much better sense of what would actually happen if the slope failed. To be clear, I'm not telling you that 7 feet is nothing. The USGS is explicit that waves of that size could still pose a real hazard to nearby shore communities, and if you happen to be in a small boat or standing on a docking quay when it arrives, a 7-foot surge into a harbor is a genuinely serious event. But the gap between a 30-foot wave slamming directly into a town and a 7-foot surge rolling into a harbor is the difference between a disaster movie and an emerge NCOI you can actually plan around. That correction is the part of this story nobody clicks on, which is probably exactly why you've likely never heard about it before now. All right, the question I get constantly in the comments whenever I cover something like this is whether any of it is actually normal, or whether something genuinely different is happening right now. The honest answer splits into 2 parts. Part 1, Barry Arm. Right now is quiet. As of early this July, the Alaska Division of Geological and Geophysical Surveys has it sitting at Alert Level 1, the baseline level described as stable or moving slowly, W, with deformation staying under 50 millimeters a day. That's the lowest rung on the entire ladder. Every monitoring instrument at the site is currently reporting, except for that one water level sensor at Point Doran. Nobody is currently on standby for an evacuation. Part 2, and here's where I'm not going to soften anything. Jackie Kaplan-Hauerbach, a geophysicist at Western Washington University, put it about as plainly as it can be put. Landslides are notoriously difficult to anticipate. Dennis Staley at the USGS has said it's genuinely hard to pin down a specific trigger. And Brentwood Higman of Ground Truth Alaska, who has spent years studying exactly this, has said it's frustrating how little is still understood about how these systems actually behave. 3 researchers who study this professionally, all essentially telling you the same thing. Monitoring can tell you a slope is moving. It cannot tell you what hour it finally goes. That's the honest current state of the science. The conditions inside these fjords are shifting faster than anyone's current ability to forecast them precisely. And anyone offering you a firmer answer than that is probably selling you something. So the watched slope and the unwatched slope ultimately end up in the same place scientifically. Nobody can name the exact hour. What monitoring actually buys you is those 20 minutes. At Barry Arm, the model indicates the first W. AVE energy reaches Whittier roughly 20 minutes after the slope begins moving, and there's hardware sitting on that slope, and in that water that would register the movement the instant it starts. 20 minutes is enough time to sound a siren, clear people off the docks, and send them uphill. Tracy Arm had 0 minutes of warning. The only thing standing between that particular morning and a very different kind of headline was simply the hour it happened to occur. And Barry Arm certainly isn't the only site like this. There's an active slope above Portage Glacier currently moving. Ton Fjord saw a major event back in 2015. Surprise Glacier and Peterson Glacier both produced events in 2024. Tracy Arm was last August. That's 5 separate sites in a SINS. Geel State inside roughly 11 years. And the level of exposure has been climbing at the same time. Tracy Arm alone draws something like 500,000 boat-based visitors a season, along with more than 200 cruise ship visits. Alaska overall takes in Rook HLI 2 million cruise passengers annually, and a large share of that itinerary is exactly this kind of experience. Sail into a narrow fjord, get close to the glacier, hold position, take photographs. It's precisely what people are paying for. So here's what's actually within your control. If you're booking a glacier tour anywhere in Alaska, ask the operator one specific question before you commit. Do they actively follow USGS and state advisories on landslide hazard zones? And have changed any routes since August 2025? Operators who take this seriously will have an immediate, specific answer for you. The trademarked 26 Glacier cruise departing out of Whittier, for instance, reconfigured its route entirely to bypass the Barry Arm hazard area. That's what a genuinely good answer sounds like. The alert levy, itself, is public information. The Alaska Division of Geological and Geophysical Surveys posts the current Barry Arm status, and the USGS publishes its findings openly as well. If you're going to be traveling through Prince William Sound, check it during the week you're actually traveling, the same way you'd check a marine forecast before heading out. It costs you a minute of your time and absolutely nothing else. On the water, the correct response to a landslide tsunami is completely different from an earthquake tsunami. There's no early warning siren for this, and there's no 10-minute lead time built in. If you're in a small boat inside a fjord and you hear a roar or you see rock actively coming off a wall, head straight for open, deep water, away from the shoreline entirely. Waves like this are at their absolute worst right up against a wall, and dramatically smaller out in the middle of a wide channel. On shore, the rule is even simpler. If the ground shakes, or you heck, are it happening, you go up. Not along the beach, straight up the slope immediately, and higher than probably feels reasonable in the moment. The couple who survived Lituya Bay lived because their boat happened to get lifted directly over the spit rather than driven into it. That was luck. Elevation, on the other hand, is not luck. It's a choice you can make ahead of time. More broadly, the reason I keep returning to material like this is that the gap between people who actually have a plan and people who don't is enormous, and it costs you essentially nothing to close that gap. If you want all of this organized in one place, exactly what to have ready, what to do in the first hour, who to call, how to get your entire household aligned on the same plan, that's exactly what the Emergency Preparedness guide linked in the description covers. It's priced at $17, and it's the same material I hand to my own family members and use myself. It's written to be read once and kept close by for whenever you actually need it. Where I've landed on all of this is here. The tallest wave ever recorded on this entire planet happened in a place where 5 people were caught out on the water and 1 boat got physically carried over. A forest. Last August, the second tallest wave ever recorded happened in a fjord that roughly 500,000 people visit every single summer, and it struck at 5 in the morning before the boats had arrived for the day. The wave itself hasn't gotten any smaller over time. The number of people standing in front of it has gotten bigger. I'll be tracking Tracy Arm going forward, the alert level, the deformation numbers coming in, and whatever eventually comes out of the continuing Tracy Arm research in science. If anything moves, I'll cover it, and I'll show you exactly where the information came from when I do. If this was worth your time, go ahead and hit the like button. I'm honestly not chasing a number with this one. It just L's the algorithm to put this in front of somebody who's got a Prince William Sound cruise booked for next July and currently has no idea any of this even exists. Take care of each other out there and stay safe.